We will next hear from Hal Finney.
I want to prove to you that I know a message that hashes to a given hash value using the SHA-1 hash. I don't want to reveal anything about the message to you. It's a zero-knowledge proof, and I've written a program to do this, which I will tell you about. Here's the basic model that we have. Peggy the prover knows the message, and we have Victor the verifier that she's going to make this proof to. So she sends a commitment to the message over to Victor, which locks her into the message without revealing any information to Victor about it. Now what we're going to do is she's going to go and calculate the SHA-1 hash on this message, and Victor is going to start with the message commitment, and he's going to calculate simultaneously with her a commitment to the SHA-1 hash. She's going to help him do this as they perform the calculation together, but of course again without revealing any information about the message. At the end, she has the hash, Victor has the commitment to the hash, and she'll open the commitment. He can verify that it matches what he calculated, and that's how he'll know that this was the message that she knows the message that hashes to this value. The motivation for doing this, lots of the presentations that we hear about will say, this particular protocol could of course be done with general purpose zero knowledge and perhaps multi-party computations, but those techniques are inefficient or they're impractical. So I wanted to find out just how inefficient, just how impractical they really are. I picked SHA because obviously there's not going to be any kind of an elegant zero-knowledge proof of a SHA hash, because the whole algorithm is designed to be complex and irreversible. So it's really meant as a benchmark to see what the state-of-the-art is for zero-knowledge proof systems that can handle general and irregular problems like this. The proof system that I'm using is one by Kramer and Damgaard. It will be presented this Thursday, right here in Crypto. Zero knowledge proofs for finite field arithmetic. It's very efficient and it's quite flexible. I've implemented two of the generators they describe in their paper. One which is suitable for zero knowledge arguments, where the prover's privacy is protected unconditionally, and the other for zero knowledge proofs, where the prover is unconditionally bound. It depends on what model that you're using. A nice thing about their system is that you can either do commitments to values up to the size of the group order in these discrete log systems, or you can do bit commitments, which are just the value commitments restricted to this range. And I make use of that quite a bit in my program. And another nice thing about it is it allows pre-computation of the commitments. The prover and the verifier can work together and calculate a pool of bit commitments ahead of time, which is relatively expensive. And then once they've done that, they can go through and actually perform a protocol in a relatively short period of time, as you'll see in the results. Relatively. Just a brief description of what SHA-1 looks like. Not going to try to really describe it, but just give you an idea of what operations are involved in it that we have to be able to simulate. The message, in the case that I'm doing here, the message is known to fit in just one SHA-1 buffer. So there's that amount of information is leaked about it, but it does not the actual length of it. The message is padded in this 512-bit buffer, which is then treated as 16 words. The rest of this W array is filled up. It's an 80-word array of 32-bit words, using each of these entries as a result of 4 XORs of earlier entries in the array and a rotate. So this creates the W array, which is where the input comes from. Then the actual SHA compression function works like this, and we have 5 32-bit words which hold the state. These get processed. The main thing that happens is this big 5-way addition. There's 5 values that are brought together in an arithmetic sum here, modulo 2 to the 32. We bring in a value from our W array, there's a round constant, and there's this function f, which is takes 3 of the words as input, and it's either selection, parity, or the majority function. And then these are done bitwise arithmetic, whereas this again is modulo 2 to the 32. So that's where it's helpful in the Kramer and Damgaard system that you can do both kinds of calculations. So the plan is we'll transform the program. Instead of having our variables be 32-bit variables, they're arrays of bit commitments with 32 entries. So each variable that we saw there is now an array, but it's still a single variable. It's all written in C. And then when we need to, we'll translate those to the value commitments. Well, what we end up doing then is that we'll have parallel execution. The prover is executing the code, the verifier is executing almost the same code, and so they're working together, as I showed in the earlier slide. And what I've got is a library of the primitive operations on these bit commitment arrays. We have Boolean and arithmetic operations. So you translate the original program, which has straightforward arithmetic, and you substitute for those function calls into the library to perform the operations that way. This is all done using CryptoLib, which had I/O operations on large integers, so it was really convenient. I'll show you just a little sample of the code. I'll show you both in the form in which it's used in the zero-knowledge proof and in the form in the original form, so you can side by side and see what kinds of transformations have to be done. Originally, this is just a fragment of the compression function. Here's where we're doing the add function. There's the 4 different types that are used. And here's the big add that I showed, where there's 5 values coming together and being added. So the corresponding code over here, once we've converted it to work with the zero-knowledge proof, each of those operations has become a function call. Here's that 5 operand add, and I now have a function which adds the 5 values, so that's the kind of substitution that you have to do. And so, the real question then is how long will all this take, and how long does it take to execute? So pre-computation, as I described, is relatively costly. This is where we set up a pool of bit commitments between the two sides. For the case of a SHA-1 argument, where the prover is privacy is protected, it takes 40 minutes to calculate that on my machine, which is a 200 megahertz Pentium. 6 megabytes of data is exchanged. And then when you actually go to the protocol, it only takes 100 seconds with 22 kilobytes. The zero-knowledge proof takes about twice as much resources. So if anyone is interested in seeing how this stuff works, this is my email address right there. And that's it. Thank you.